Hello, everyone. Thanks for joining for today's talk, Blockchain Innovations, AI Integration and Security Trust by Professor Daswin Silva and Yuhong from Santa Clara University. And this event is co-hosted by IEEE Computer Society chapter, along with our Blockchain chapter. And a little bit about me, I'm Revant, IEEE Silicon Valley Blockchain chapter chair. I will give brief introduction about our group and also our mission and fast and future events. And also we'll talk about a little bit about community engagements and tonight's talk, uh, introduction and agenda. Our group was started by Olga and Paul in 2022, and they were supported by Dr. Ramadas, who is currently co-chairing main IEEE subgroup blockchain, and Young, researcher from Santa Clara University. I'm now chair, and I'm closely working with other teams to build community here. And our mission is to bring people together and create the future by supporting blockchain innovation in Silicon Valley and Bay Area. And we mainly focus on exploring and discussing new blockchain advancements and various application use cases ranging from cryptocurrencies and blockchain protocols, layer 2 solutions, smart contracts, blockchain Oracle, DeFi, NFTs. We also advocate for responsible use, build network of diverse professionals here, and leveraging our unique position for global impact. Our objective is to promote blockchain technology innovation, sharing knowledge through events, meetups, and reading groups in Silicon Valley and Bay Area, aiming to serve Tri-Section 1's IEEE Santa Clara section, and planning to in the future also support Oakland, East Bay, OEB section, and San Francisco section. And these are some of our notable previous events. And since we started in 2022, we have been having 2 events every year. And we had 2 events last year. And prior to that year in 2022, we had 2. And we're planning to have for more in coming years. And also, we're looking for some volunteers to help us to conduct more. And these are the names. And as you see in the future events, and one today what we're having is blockchain innovation, AI integration, security test, and another one we have plans to conduct in October. We are in talks with UC Berkeley. It's almost finalized, and we'll give more information on this. And coming to community engagement, we host monthly meetings or quarterly meetings with guest speakers. This includes in-person and web-based events. We also plan to organize networking gatherings in the future. Additionally, we conduct workshops and lectures on the blockchain advancements, protocols, various other technical concepts in field, as I mentioned earlier, layer 2 solutions, and blockchain oracles and NFTs. We often collaborate with other IEEE chapters outside professional and educational organizations here in Bay Area. And lastly, we have multiple communication channels for outreach and engagement. This includes LinkedIn, Twitter, YouTube, Luma, Meetup groups, IEEE email distro where public can subscribe to get email updates. And more importantly, we are actually looking for volunteers if anyone interested. And also, we are looking for active speakers as well in the future for future events. Please reach out to us. Thanks. And lastly, we have multiple communication channels for out. Without any further delay, let me talk about today's speakers and today's agenda for this event. First speaker, Professor Daswin Silva, he is here, and he is a deputy director at Center for Data Analytics and Cognition at LaTrobe University, Australia. And his research involves artificial intelligence, data analytics, automation, ethics of AI, and some of his notable achievements are National Recognition for Teaching Excellence in AI 2021, and Vice Chancellor's Award for Teaching in 2019, and Mid-Career Research Excellence in 2018. And he has published over 100 research articles with significant impact in this field, AI and data analytics. And also he holds several key positions within IEEE organization. And in today's talk, blockchain and AI for industrial applications. And we have Yuhong from Santa Clara University. She is Associate Professor, Department of Computer Science and Engineering at Santa Clara University. And our research involves trustworthy computing, cybersecurity, online social media, IoT, blockchain. And some of our notable achievements, as you see here, IEEE Computer Society Distinguished Visitor 2022-2023, and Distinguished Lecturer in 2021 and 2022, and Associate Editor for several prestigious journals, including IEEE Transactions on Service Computing and Blockchain, Research and Application Journals. And today's talks, Facilitating Security, Trust Among Multiple Parties Through Blockchain Techniques. And she is our program committee member here. And today's agenda for this event, session on blockchain, AI for industrial application by Professor Daswin, followed by Q&A session. And short break we will take, and visas will be here soon. Facilitating security and trust among multiple parties through blockchain techniques, section by Associate Professor Yuhong, and followed by Q&A sections. And I will have closing remarks. And online participants, please post your questions on chat. We will actually look into and respond. Thank you so much. And over to Professor Daswin.
So am I audible? Yeah, good. All right. Okay, thanks everyone for being here. So I'm Daswin, and today we'll talk about blockchain and AI for industrial applications. Yes. Yep. So first of all, thank you to Revant and the Silicon Valley Blockchain Group for organizing today's event, and also to Ramesh and Gora and the IEEE blockchain technical community for facilitating the introductions, and also, of course, the IEEE. So I have a fairly strong connection with the IEEE. So I'm a member of the Industrial Electronic Society, where I hold 4 positions, which keeps me quite active outside what I do in my day job, and also in the BCTC. I'm a governing board member and an associate editor of 2 journals of the IES, and also recently I've organized the first IES Generative AI Hackathon, which was quite successful. So across the world, we had many submissions and also lots of conference type of work. So a bit of an agenda. So lots of introductions, myself, and then AI, and then blockchain, and then the integration of blockchain and AI. And then we look at responsible AI. So we're sort of carving a path towards the role of blockchain in building AI, and also how blockchain can be used for adoption of AI, or promoting a more responsible adoption of AI. And then I'll switch into the IES areas of interest, which is broadly the technical committees in the IES. And then we look at industrial applications, specifically 2 areas which my research lab is focused on, one in energy and one in robotics. So you'd think that they are further apart from what blockchain is able to do, but there's novelties and innovations that are possible. And also neuromorphic, which is related to the talk I'm giving tomorrow. And that is an area of huge growth potential. So small AI versus the large AI. Or energy efficient AI, and there's a lot of focus on building small AI, as we heard in the Apple Intelligence media release just 2 days ago. So the A is for artificial in this case. So that's the agenda. So just a little bit about where I'm from. So LaTrobe University, fairly large campus, similar climate or weather to San Francisco. So lots of wineries in Melbourne, and also bushfires, unfortunately. So there's so my university is a fairly large university with about 5 campuses, and this energy AI project is based on the 5 campuses and energy consumption across 200 buildings. This project was well received by the Times Higher Education Impact rankings, in alignment with the UN SDGs, which is a lot of research projects, research groups, or even researchers align their research with the SDGs to show the impact. Research impact is different to publications or grants. Impact is where there is an actual social, economical, or commercial impact on community and society. So this project has impact, and that's what came out in the impact rankings. And it is built using a lot of AIs. So that link will take you to some of the information. So leap-ai.info, so which is LaTrobe Energy AI platform. And LaTrobe was the first governor of Victoria, where there's a statue upside down for some of his misdeeds while he was governor in Victoria. It's a long time ago. That's my research center. I'm just going to keep this light because you've heard some of this detail. So just as any research center, we do fundamental academic research leading to publications and grants, and then we also build technology platforms like Leap based on this, and we apply these into different areas, and we also teach. So I conducted a very successful micro-credential program, which is sort of maybe not so new in San Francisco, but kind of new elsewhere in the tertiary education sector. So before developing a subject, you teach the course in a very short, intensive format, online to maybe a targeted audience, and in this case, it was industry. So we teach AI to industry, and then we find out or evaluate how well that performs, and then we take that into an awards degree or an undergraduate or a postgraduate course. So that's something else that we do as well. You've heard about me, so I'm just going to skip that. Industry partners, don't think, except for Toyota, none of these companies might be familiar to you. Yes, so we work with a lot of industry partners, and that's where the industry partner brings in funding. And that funding is used to find a really good PhD student who will work on the industry project, not across the 3.5 years, but in shorter sprints. So I sort of follow an agile approach where the research and the industry partnership both benefit from the PhD program, or if it's a postdoc, similarly as well. So coming into AI, just very briefly, I'm sure everyone's heard of AI by now and have their own experience of GPT and the like. So this is transformational, in fact. So late 2022 was when OpenAI dropped ChatGPT, and sort of the whole world changed. Tertiary education, especially, is struggling to figure out policies for academic misconduct, which we still don't have, because any plagiarism detection, AI plagiarism detection is not as is not strong evidence for the case, and that means we have to change how the assessments are written, so authentic assessment. So why AI? Because AI learns faster than humans. So by some measures, we take for very specific use cases applications, AI or ChatGPT learns in a couple of months, but humans take a good part of our lifetime, so primary and secondary education, to figure out not everything, but some areas. So it learns a lot faster. Even Jeffrey Hinton said that backpropagation, which is his algorithm, is a far more evolved learning technique than what happens in our brains. It's simple and effective. So for about $20 per month, we can get really good AI. And this was not the case well before 2022. Building AI was expensive, and that's why no one really invested in it. So companies did not invest in it. And you'd have to bring some good research into building a bespoke solution. It's not, and it's usually one size does not fit all. Where so one company builds an AI solution, it's not easily transferable to another company. And that means the cost of implementation or the scale-out cost was quite significant. And it's also proposed as a general purpose technology. So I think you're familiar with general purpose technology for things like the internet, the smartphone, or the personal computer are transformational. They change everything across the economy. So one aspect of this is inventions. So the technology itself leads to other inventions. So on top of ChatGPT, there's so many other applications that have been built that it's sort of countless. We can't really count how many different innovations it's led to. And so that's general purpose technology, and that's why we should be concerned. So we had some sort of digital transformation. So blockchain was part of this in 2015 and so on, where the likes of Web3 and some parts of social media was part of the digital transformation. So now this is on steroids. It's a bit of an AI transformation. And there's a couple of studies related to the negatives or the risks, which the primarily workplace automation or job loss. So this is one estimate where it's not the occupation that's automated, it's the tasks attached to the occupation. So if you read these studies, they unpack the occupation. So if it's software engineer, or if it's admin, professional staff supporting admin functions, or if it's a speech writer, you break down the tasks, and then you find that at the task level, there is a lot of automation replacement that can happen. And that's it. And this is another reason why we need a responsible approach. So governments, companies alike should not take the shortcut sort of uber capitalist path where it leads to job losses. But where there is job losses, there's also skills training, or another company is finding opportunities for those workers who have lost their jobs. So there's significant risk from that end, but it is also proving to be a lot beneficial, useful for many other applications and purposes. So if you think of the three greatest challenges across the world, so more global south than north, so healthcare, education, global poverty, and the significant informational uplift using the likes of GPT, where translations will work, where smartphone applications can be very informative to find relevant, applicable information for people at different levels of education. So those who haven't completed school or those who are fairly older. So there's lots of potential in that space, and that's where the benefits outweigh the risks. And AGI might be around the corner. So interesting, last year, Google DeepMind defined the AGI, which is sort of maybe a bold or ambitious, overly ambitious effort, but they defined it in terms of 3 or 4 dimensions. So AGI is sort of the next one. And well, the debate is, it's an open-ended debate what actually exactly happens at OpenAI, closed AI. given that there was a CEO, the saga related to the CEO removal and reappointment. So this is interesting. I won't go into the details. That's from 1968, Marvin Minsky, potentially the parent of AI or modern AI. And then in 2023, we have this from the OECD. I think you know the OECD. So this they released that they tried to define AI in early 2023, and then there was a lot of criticism of how they defined it, and you can see all the crossed off and the bold parts, and now they're trying to explain why they've defined this. And this is the OECD has consulted maybe 100 AI experts from across the world, and even for those experts, defining it was met with a lot of criticism because this is not the experience of AI for the average consumer of AI. Or the academic researchers or the commercial applications. And that shows the challenge because intelligence is a moving sort of piece. And it's also opportunity for the likes of blockchain to bring some standardization into AI. So there is that opportunity indicated there. Another common misconception with the difference between machine learning and AI. Has anyone come across this where some conversations or some content will refer to AI and ML? So machine learning at the moment is the best form of building good AI, so learning that leads to intelligence. But then if you look at human intelligence, that last dot point, that's not the only intelligent faculty that we have. We have things like perception, reasoning, memory, recall, planning, expression, and so on. So these are not artificially implemented. So there's no computer algorithms that have good, there are reasoning algorithms, but they're not as good. They're quite primitive. The same can be said of machine learning from 20, 30 years ago. They were learning very simple things like, if you've heard of the MNIST dataset or the IRIS dataset, so very simple classification tasks, but which is not the case. So we have learning on steroids, so quite augmented with the recurrent learning capability or the transformer algorithm that is foundational to a lot of the generative AI. So this is a common misconception, the difference between the two. But then if you think of AI as an outsider, so if you think of AI as a blockchain expert, what is the value there is in what it can achieve. So I call these AI capabilities. So it's not machine learning that is useful in an application. It is something else. So that capability is either a prediction or forecast, a classification or a detection. So face detection or anomaly detection or spam filtering. That's a classification. Association is a grouping, so customer profiling or energy profiling, so groups of similar behaviors. Optimization is scheduling, so finding the shortest path for some sort of delivery or find the most optimized circuit design for that sort of setting. And more recently, we have a fifth capability. Does anyone know what this is? Which is the generation. So generative AI, it's neither of these. So we generate new content. So GPT, DALL-E, and AlphaFold are the three main ones. And there are frontier models that generate really well. And there's smaller models that generate not so well. So this paper, bit of self-promotion, authored by me, which co-authored, which gives you an idea of how the capabilities extend into applications. So prediction of demand, revenue, that's more commercial, or prediction of energy, prediction of COVID cases, that sort of different applications, and then the different algorithms. So there is an ocean of algorithms. There's too many algorithms for different tasks, and this was one of the challenges back then. Before generative AI, we didn't know which algorithm to choose, and different algorithms had different results. But now we have the frontier models providing foundation to build our innovation upon. So if you followed the whole generative AI conversations, there's been industry-specific GPTs or LLMs like, say, Bloomberg for more financial data. That is very early, so early 2023. But then GPT-4 defeated Bloomberg on so many different metrics. But GPT-4 was not trained on financial data. So this is a strength of frontier models where they don't really need custom data to produce sort of unexpected outcomes. So it is intelligence in some forms. And that's why we don't have to decide between algorithms. We take the frontier model and we try to fine tune it, retrain it, or even so prompt engineering is another techniques. So there is a complete different approach for leveraging how AI can be useful in applications. Yeah, this is in the same paper, how to build good AI. So a bit of an AI lifecycle with a lot of focus on data. But then this was before generative AI. So now we have a lot of the data captured inside the gen model. So we build upon the gen model. So different approaches, but this is, I think it's still useful. I spoke about this. So the distinction between narrow and generative AI generates new, complex, and meaningful output. So narrow AI is prediction classification. Those four. Generative AI is quite different. And because it generates content, it can be used to generate anything. So text, we start with text, images, audio, video, code, hybrids of text and images, text and video, and so on. So there is a bit of a spectrum. This is my position on how things are developing. So we have what used to be good AI. It's called it's narrow AI, conventional AI now. So the likes of face detection, self-driving cars, that's all constrained. It's goal-oriented. There is a specific task to be solved, and there is no generalization of intelligence. And then now we have generative AI. So the likes of this, Santa Claus taking selfie in front of hurricane. So that sort of image does not exist. That means it was created. It looks meaningful. It looks human-like. So we accept it. And that's generative AI. And then AGI is the next iteration. By some estimates, it's well, if you ask Elon Musk, it'd say next 5 to 10 years. If you ask someone else like Jan LeCun, it'd say 30 or 40 years later. Jeffrey Hinton is a bit quiet about this. But the coffee test is interesting. So this is a potential hard AI, so an AI-powered robot that can randomly walk into any house on any street, figure themselves into the kitchen, and make themselves a cup of coffee. So a lot of information processing there. Not just navigation, object identification. There's a bit of nerve sort of thing that will help them to recognize. But the whole activity of conceiving, I have to figure out which house, which ingredients, and the process of making coffee. So, or it can be coffee or anything else that can be made in the kitchen. So that is a test for AGI. And then there's further down, then there's science fiction of super intelligence. What we've seen in the films. So that's a roller coaster introduction to AI very briefly on the surface. And now we look at blockchain. So I have some experience in the past working with distributed systems. So I look at blockchain from that distributed lens. But I understand through many conversations, there's other lenses that researchers, experts look at blockchain. So for me, this is a single notion that has many different implementations or manifestations. So I call this one child, many parents, or many parents, one parent, many children, where so fundamentally distributed ledger technologies, which manifests as a blockchain, as a crypto, as a smart contract, as an NFT or a token. I quite like the original definition for blockchain. So electronic cash was the focus. And then that's the one child, many parents. That is one very clear application. But then gradually it's transitioned since 2008 or 2010 when it really hit the scene. I like how the NIST has defined this. So distributed digital ledger for transactions that are grouped in blocks. But then the OECD more recently. So I think there was a bit of a peak in 2015-16, and then there was a lull. But it's sort of, there's been a resurgence. There's a fair bit of work happening in terms of building or applying blockchain for some of the dirty problems or hard to solve problems. So the OECD had a good description of this in 2019. Traceable record keeping, and I'm picking on keywords because I'll bring this together, I'll converge these with AI in the next few slides. So traceability is something that's missing in AI, and that's where there's a whole trust issue. The bad reputation is because AI is opaque, or what used to be called black box models. We don't have a clue of what's happening inside the model and how it generates the output. So its traceability can transition quite easily into explaining what happens in AI. So that's a good position. So this is potentially one of the challenges in blockchain, where different groups have different interests in the technology and they pull it in different ways. So there isn't a sort of a common platform or standardization to help push good research, good applications forward. This is another good indication. So I think you're familiar with Gartner hype cycle, hype curve. That's from 2022. There's a lot of blockchain there, and then in 2023, they're sort of missing. There's not much there. I think it's shown as things like cloud platform. So there was something else. Come back. Yeah, there's quite a bit here in 2022, but it's missing in 2023. So that's some indication where there is a lack of clarity in how to use the technology, especially from industry, because Gartner is more industry focused. But having said that, if you look, if anyone is looking for an interesting research question, if you go back 5 years and look at the hype cycle and see what actually came into fruition, you might find there's lots of gaps in Gartner research as well. But lots of well, across the world as a bit of an indicator or a benchmark. So question to the audience: so is this a common challenge in your experience, that we have very good, successful prototypes or demonstrations of blockchain, but then there is a bit of a limitation of sustained practical application? So one example is the Latin American and Caribbean blockchain initiative, which was quite active until about 2022. And they had a lot of funding, but then since 2022, it's been fairly quiet. They actually had a counter of how many blocks and how many transactions on the LAC. I think it's a LAC chain. So one of the challenges is scalability, and this is also a pain point for bringing blockchain into AI. So transactions per second. So one comparison is Visa credit card systems process 45,000 transactions per second, whereas Ethereum will process 30 transactions. Significant gap between the performance or the speed expected, and things have to move fast. So this is because the proof of work method of validating blocks, which is very secure and lucrative for those working in that space, but it slows down things dramatically. So there's a transition into proof of stake and other proofs, which may increase this, but the evidence, the practical value of this is still to come. So that's a sticking point for bringing blockchain into AI, the speed of operation. And everyone's had their ChatGPT experience. So it runs on steroids. It runs on a lot of server compute power to give us those answers very quickly. And even if you push in a 2-page prompt, which we've tried in our lab, the answers are very fast. So it reads all of that and processes things quite fast. But that speed is not where the whole neural network is not run. They do a lot of optimization under the hood, and that's how they get that level of response times. So the same opportunity lies for blockchain as well, to process things faster through different optimization algorithms. At the enterprise level, Hyperledger is sort of benchmark or state of the art in my experience. And then recently the Joint Financial Management, so more locally, and the US Treasury Financial Management Improvement Program, I think they have a really good, this was recent, 2023, I think. They have a really good report on, again, a prototype, how they used blockchain to find out federal funding allocations from federal bodies to non-federal entities. And then the whole smart contract, there's code in there that gets executed inside the block, and how that can be used to check if the funding has been spent properly by the receiving entity and so on. The US Navy, this is obviously classified information which we can't find easily. So paranoid blockchain is to secure software engineering, trying to make sure that there is no hacks or breaches in their software platforms. The European blockchain services infrastructure, again, there is a lot of strategy talk, but there isn't really an implementation, which is surprising given Europe adopts and builds things fairly fast. And then blockchain-based service network in China, which interestingly does away with all the crypto features, and it's purely transaction focused. And then the LAC chain, which I mentioned, which was quite active, but then now it's sort of slowed down. So if you think of DLT more broadly, bird's eye view of opportunities and challenges on the left, on the right, opportunities, on the left, challenges. It's right at the top, innovation. So we can, it's transformational, just like AI. We can change the whole trusted third-party situation for many interactions. So government, legal, healthcare, financial, productivity. So that leads to productivity improvements, resilience, transparency, data integrity, accountability. Most of these explain themselves. Financial inclusion. So this is more world challenges. So there is equity and transparency in financial transactions. Consumer protection and responsible industry businesses. So responsibility is that traceability of what went where. And we see a lot of this in supply chain, but there is a good opportunity for industrial systems, so factory automation and the like, to adapt to this, but then scalability can be a sticking point there as well. So the challenges starting with scalability, and then the full autonomy of executing smart contracts without human supervision. There's a couple of major issues recently with this sort of implementation. So that is a challenge, and this is a challenge also for AI. We always want this human in the loop situation, but that does not come at, especially for AI, does not come at the cost of speed. So similarly for blockchain, there can be innovations to make sure that the response time is sustained while there is human supervision. Data privacy and security. So this is for public blockchain, which will bring lots of people together, but then obviously has privacy and security concerns. And then the last three, interoperability and regulation standardization are, so interoperability with legacy systems. A lot of the AI will be similar. So AI goes into the legacy system, whereas blockchain tends to stay outside and try to change the whole system. So there is a challenge there that needs to be overcome. How can they cooperate or connect with existing systems? Regulation is another challenge, which some of the government entities are working towards. Standardization is another challenge. So which technology where, so that the one child, many parents sort of situation. So if you look at the alignment between blockchain and AI, so I go back to the fundamentals. So AI is making machines do things that would require intelligence if done by humans. That's the 68 definition. But if you look at the capabilities, prediction, classification, association, optimization, generation, and then blockchain is very simply, it's probably one-dimensional, a digital ledger for the transfer of value and data. So you can transfer transactions of value, transactions of data. And then data is a sticking point for AI. So there's lots and lots of data required to build good AI. And in some studies that compared the different algorithms for generative AI, the algorithm was had a very simple contribution to the quality of the AI, whereas the dataset has a huge contribution to the quality of the AI and the quality of the intelligence capability. So if your dataset was in the billions, really good AI compared to in the millions. So this is huge scale, lots and lots of data. So much that we don't know how much data OpenAI is using. And that's become a company IP, in fact. And this data needs to be managed and processed effectively. So we can get much better AI. So at the moment, assuming the data that OpenAI uses is collected through maybe not so ethical means to get really good data, because AI already has a bad reputation in the public domain, and then people are not willing to share their personal information or behavioral attributes, that sort of lifestyle choice and that sort of data easily. But hypothetically, if we had access to really good data that represents human activity at scale, either in a professional setting or a personal setting, then we can build really good AI, because good data builds good AI. So we need pun not intended, that we need an intermediary between good data and good AI, and that's potentially one opportunity for blockchain, where the blockchain regulates how the data is used, which model uses it, and also brings back some compensation to the data provider, because in the current conversation, the consumers of AI or the providers of data, we are completely missing. There is no data ownership in how the AI is trained. And this is something the likes of the EU, the European Union AI Act is looking at. So how can individuals who contribute data be rewarded for what the AI companies are sort of profiteering from our data? So that's a really good opportunity. And then the models. So AI is not trained once and then it stops. So we've seen GPT, if you follow their, if they follow their the company journey, there was GPT-2 quite early, which was very nonsensical garbage. And then 3, 4, 5 for this plans for 6 and so on. So this showcases that AI is always evolving. It's not, intelligence is not a one-off, just like we continue to learn. And that's in our sort of limited scope of learning. But the world, all of us and the machines that we use produce billions of data per second or per week. And that means the AI continuously has to evolve, just like the internet. So GPT-3 is only updated till, which no one uses now because it's only until 2022. And we all want information that's current. So we're looking for GPT-4, for example. So the models have to be retrained and calibrated quite frequently. And the model management is also a traceability, a trust-related activity, where the models have to be managed in a persistent, traceable, sustainable, responsible manner, which does not happen at the moment. And we're sort of we are at the poor receiving end of whatever the AI big shots throw at us, we start using, because we don't have a bargaining power of which AI model should I use and how much should I spend on this. So it's a $20 flat fee. And we don't really even know if you're using GPT-4, because behind the scenes, it could be anything else. So this transition of some control or some transparency really into how the models are used by different individuals is something, again, we need the colloquial intermediary to negotiate for us. So we could be using just one part of GPT, for example, for some of the functions, and then we could potentially ask or demand for transparency in what kind of AI we're using. So just like explainability, which is the whole opaque AI model can't explain the outcome. What's happening now is we can't explain where we are getting our intelligence from. Just because it looks good, we accept it. So we're sort of in a compromised situation, if you like. We don't have bargaining power for what we're using. For example, if you think of email, we have more control on email than we have on AI, because we can decide which provider, we can decide where the email, which data center is using that, where the emails are stored. So similarly, it's a service, it's a soft service, but we don't have that bargaining power. And the blockchain potentially can shift that balance more towards the consumers. And then finally, trust, and this is one for the companies. So AI has obviously a bad reputation of being not trustworthy. So rogue training data, opaque AI models, and autonomous decision-making. So blockchain maybe has a trust issue as well, because we're replacing the intermediary. But then maybe together there's, again, research potential, innovations to be discovered, sort of. How can we address the trust issue into complementary technologies and bring them together? So if you think of alignment, there is alignment in the data, in the models, and then in trust, how trust is developed in the technologies. So just in my opinion, what I might say are the grand challenges are how can blockchain empower AI model training and development? So that's building the models. So integrity of training data. So how do we know there's good quality data going into the AI models, the frontier models? The blockchain can have this traceability trust factors built into how the data is received, ownership of personal data. So that's the custodianship that I've contributed X number of data points to build OpenAI, and I'm getting rewarded whenever it's used. Hypothetical imaginary situation, which might not occur in our lifetimes. But that is possible if we have a reliable, persistent transactional data management solution, which is more managed in a distributed manner. Data as an asset for trading. So this is more futuristic. Just like we trade stocks or energy, we can also trade data that we might have data projects in our universities or companies where we collect, where we have certain mechanisms to collect data, and then we can trade this as an asset for building better AI. So how does that trading happen? Potentially, that's again another question for blockchain. Model evolution, so model persistence, model ownership. So if you're an AI researcher and you want to contribute your model to the likes of GPT to make it better, or to make your model then how can you have some record of your contribution, and how can you be compensated potentially if it's an effective, integration of models. So again, good application potential there. And then responsible, so trust, traceability, and explainability are the 3 points that I would touch on for responsible. So on that note, there is a lot of talk about responsible AI, and potentially another buzzword to the mix. But it's AI. What used to be AI ethics is transitioning into responsible AI. And then again, another quote from way back. So Von Neumann sort of predicted this eventuality where it's a two-paced situation where the technology moves a lot faster than regulation can keep up, and we are seeing this every day. So the likes of deep fakes to soft fakes. So there's no regulation governing either of those, especially in Australia. There can be so the opposition party can create a fake video of the prime minister talking nonsense, and there is no regulation to stop this or question this at all. So AI ethics progression. So GDPR did a really good job for data ethics, and we likely see a similar situation with the AI Act, which comes into effect early next year in the European Union. And then the IEEE also has this ethically aligned designs. That's an AI ethics piece, really good work. Lots of people came together to build these. But then, and then there was a boom of AI ethics frameworks, more than 100. So Rolls-Royce, Microsoft, Google, everyone had an AI ethics framework, which is also part of the problem in the industry. So where self-regulation, so AI companies should not be introducing the ethics frameworks themselves. There should be third parties doing this. So that's another opportunity for the likes of blockchain, where more decentralized regulation or ethics evaluation or ethical evaluation of AIs. So other companies or individuals who are interested in how the AI operates, they can add transactions to potential AI ethics blockchain to find out how good or bad it is in different situations. Because once it's released, we don't have a reliable feedback mechanism to see how well it adapts to different social situations, professional situations. So it's just out there. And then we might hear about something in social media, but there isn't really a standardized approach. And I see blockchain has huge potential, where if I've used ChatGPT and I had this certain experience, and then I can have something similar to a smart contract saying my experience was not transparent, not there's a lack of accountability, there's a lack of privacy or safety, and that goes into the ledger. And then you collect such data points across a period of time, and you have a certain scoring or a certain benchmark for how ethically or unethically the AI performed. So that's where the blockchain can support responsible AI adoption. So responsible AI has a number of adjectives. Yeah, and just the list keeps growing. But each of these are potentially individual considerations for good AI, and each word is important for the conversation to continue. That's just a little bit about the AI Act. So if you remember, when GDPR was introduced in 2018, we started seeing accept all cookies come up on websites. So potentially in early 2025, we'll see the same chatbots. So the moment you hit a chatbot on a website, there'll be a huge follow-up saying, you're talking to a chatbot, I'm AI and whatever. So this impersonation of a conversation with AI is something that this AI Act regulates. And just like GDPR, even if they travel overseas or if because it's on the internet, they can be held accountable. So every company will potentially start implementing these. So very quickly, it classifies risk into 3 levels. So unacceptable, high risk, and limited. So unacceptable is things like social credit scoring, real-time public spaces, biometric identification, so face detection. High risk is biometrics within well-defined settings like organizations, critical infrastructure like your smart grids, energy grids, law enforcement, education, and things. So the minimal is for fake content and for chatbots. So that's where we'll see the pop-ups coming up on websites soon. So that's a really good job, and it was passed, or it was enacted this year. Just a bit of a minimum checklist. Just skip that in the interest of time, I think. Coming into the industrial applications, so this is what the Industrial Electronics Society focuses on. And we have a life member in the audience, Michael. Thanks for making it. And I'm Paul. Oh, it's nice. It's yeah, yes. If you but that's a lot of bit conceptual. If you look at the topics of interest, we have a large number of real world application of industrial of electronics engineering, and things like computational intelligence and AI. So electrical machines, power electronics, transport electrification, robotics, motion control, standards, human factors, and so on. So I'm just going to leave this here. You can find this on our website as well. And there's a lot of AI going on in the industry space, and these are some of the leading companies we talk to at our industry forums and conferences where we come together, researchers, industry, to discuss the different kinds of innovations. That's a really good example for Mitsubishi Electric, how they can reduce time taken, improve efficiencies. This is ChatGPT. It's not released yet, ChatGPT for circuit design, which is quite a novelty. I don't think it works at scale. Just like when OpenAI drops like things like video clips, it's 1 minute. So why is it 1 minute and not 10 minutes? Because it doesn't work after 1 minute. Same here, so good demonstrations, but it shows the potential of where it's headed. So it's really good to see these and understand how this works. How much time do I have? Around time. Okay, so yeah, maybe in 2 minutes I'll talk about my projects now. So energy, well, fundamentally, energy marketplace, energy trading, and blockchain is fundamental for this, because we can bring different types of energy coming in, and the transactions, but scalability is a sticking point. The transactions happen very fast. So I'm not too familiar with the grid over here, but in Melbourne, there can be significant peak events and outages, and there can be opportunities where kilowatt hour is about $12 baseline. It can shoot up to 600. So if you have the right FCAS ready, so battery or renewables, then or a fleet of EVs, you can supply the grid, and that itself will pay for your capital cost of the battery installation. So NFTs of consumption, renewable generation, and EV charging, and then the vehicle to grid. So there's efforts in my state to materialize this vehicle to grid, where it's not just one EV, but a fleet of EVs coming together to support the grid during peak events. So morning and afternoon peak. So in this project, we're trying to compare with conventional grid operations. Simulation, we can't really implement it. So potentially we can showcase that blockchain enabled, or AI and blockchain energy marketplace has a lot of potential for this smooth operation of renewables and consumption. This is another area. So blockchain and AI in robotics. Robotics moves very fast. Blockchain is a bit slow. So that's a challenge that needs to be overcome. But here, these are the 3 factors: persistence, trust, and traceability, which is lacking in robotics. And if you have more intelligent robotics, we need to have persistence, trust, and traceability. So robotic motion intelligence has perception, control, and agent. And in the middle, there is this RMI sort of layer. And we can implement this more effectively in a distributed sort of autonomous fashion if we have blockchain, fairly fast blockchain in there. So that's another area of research that we are conducting. And then finally, neuromorphic. So potential growth area for AI, so small AI, where the artificial neural network is fundamentally transformed. It's on signals now. And if you're familiar with things like FPGA, then spiking neural networks, there's a few chips in operation. So one of my projects is with Intel and the Loihi chip. And that's what I'm going to talk about tomorrow with a colleague from UC Berkeley. So, but this is very unreliable, and there is a huge lack of traceability. So I see the same sort of highlights of what's missing and what blockchain can supply, but obviously we have to address some of those performance gaps. So just a bit of a teaser for getting started on AI. So really good content out there. A few years ago, there's a lot of noise. Everyone started to spew AI content. So Karpati has a good blog, and he teaches you how to build GPT from scratch, for example. Andrew NG is really good with industrial applications, and maybe you can subscribe to some of the newsletters. Lots happening, but if you read this daily, you have a really good sense for where it's headed. And then if you're a researcher or industry, you can really leverage on those opportunities. Okay, that's me. I think I'm forward. Thank you.
Anyone has questions? I think if people want to get their pieces out there, so do that someday. If we get these outside.
Yeah, sure. Yes.
I have a question for you. Maybe go back to the Mitsubishi slide. Do you know of some specific applications of narrow AI and blockchain in industrial applications, maybe at LaTrobe or around the industry, that you can just spend a couple minutes discussing
Oh,
what's
yes.
being used?
Yeah, good. So the two projects that I mentioned towards the end, so energy and robotics are the two industrial or practical applications that we are working on. So there's a lot of AI that we've built into energy. So this is a microgrid of 5 campuses of my university, 200 buildings, approximately 1 billion data points that we need to transition into short-term forecasting, long-term forecasting, outage detection, anomaly detection, energy profiling. So lots of AI going on in there. But we are, as a microgrid, we are unable to trade the surplus with an external party. And this is where we're building a prototype of blockchain for the energy marketplace. So why it's a blockchain and not standard server database sort of setup is because of its key attributes of it's distributed, it's managed autonomously, and it has a lot of traceability of where the energy was produced and where it was traded. And over time, that will also build trust for the buyers or the purchasers of the energy. So there is a very active FCAS market, which is frequency reserves, which is like if there is an outage, the battery farm will supply the grid at scale. One of the challenges there is it's a very short response time. So the proof of work technique for adding blocks to the chain or for the whole NFT gig does not work. So we have to look at different types of proofs or different consensus algorithms. And well, fortunately, there's quite a number of consensus algorithms that we can use. So that's the only sticking point: the scale, the speed. So it might ultimately it might not look like blockchain because we've optimized it so much to satisfy the speed requirements. But foundationally, we've started there. So we're building a blockchain for the energy trading based off this platform.
Would pretty much be narrow AI for that sort of application? Yeah,
that's right. Yeah, it's well-defined AI where the prediction, the classification contributes to how the blocks are created or traded. We also have a generative AI chatbot that tries to build prediction, tries to predict what's going to happen. So because so prediction across maybe 6 or 7 different scenarios, can we automate this? So that's another sort of work in progress.
Thank you.
Yeah, good. Thank you.
And one more question: when you're talking about for AI, as you mentioned, computation power and the data is very important.
Yeah.
Than any other thing. And since it's a blockchain and distributed system where you use like Turing complete EVMs and also using interplanetary file system IPFC. So how do you see work together to build models and execute on network, not outside?
Oh yeah, it's a good point. So building on the edge, sort of.
Building on blockchain network itself instead of. I mean, most of the time I see these prediction models or whatever they rely on these already existing models.
Yeah.
They run outside using blockchain oracles. They just use the side chains and feed that data to blockchain to take actions. Instead of doing that, this running on networks is not that easy. Every transaction costs a lot. But I don't know where it. I mean, is there any?
I haven't seen much. So building the AI in the network itself is interesting. So well, before blockchain, there was distributed AI where you'd have client server sort of thing where you'd send it to train and then you bring it together. But that sort of died out, and maybe because of the GPU thing. So for training, really, we need a lot of GPU, and that's usually a lot more efficient if it's in the central locations. That's where the GPU. So if you're serious about building AI, you buy a GPU rack, and they sell by the rack. And that's where NVIDIA is shooting for the stars. So I think that would be the performance. So in training, it's so far it's centralized, but no one. But then it's again which algorithm comes up, and potentially if there is a distributed algorithm that works well, then it could be.
There's a lot of scope where anyone can contribute their GPUs. Along with very big.
The breaking the data into the partitioning itself. It was very popular before GPU. And then yeah, things just
Makes sense. So, sorry, we have another post and you want to share the screen? Thank you so much.
Thank you.
It was very interesting topic.
Okay.
Got it, looks good.
Cool. Do you want to? Okay, can you hear me?
Yes.
Good. Okay. So shall I start now or later? A few more minutes or? Okay, so I would just start. Thanks for the prior speaker. He actually covers a lot, and so my part may actually have some of the mathematics. Hopefully, I will make it simple, stay high level. But if I accidentally go into detail, please stop me anytime. Okay. So my talk today, the title is Facilitating Security and Trust Among Multiple Parties Through the Blockchain Techniques. And I'm Yuhong Liu, and I'm currently associate professor at Santa Clara University. And here's a very brief introduction about my overall research interest. So you can see everything is centered around trustworthy computing. And I actually also cover several different domains, including, for example, I started my PhD working on social network, detecting the malicious user behaviors using machine learning. And nowadays, we are actually working on disinformation, misinformation propagation. And other than that, I also work on blockchain, for example, working on the security and the fair digital trading based on blockchain. And well, we also work on a little bit IoT security, mainly focusing on the energy efficient solutions. And also recently, the responsible AI. And it's actually quite big, but we've mainly focused on the fairness part and the privacy part. So that's a brief introduction. Actually, also recently we received an NSF grant to support an international collaboration on the clean energy for climate change. And there we also adopt blockchain for clean energy trading market, transactive energy, so that there's a lot we can talk in common. And there we also introduce AI techniques, and we want to make sure different communities, including those underserved communities, they also get fair access to clean energy. So there's a lot in common we can discuss offline. Okay, so then let's talk about today's talk. So actually, people always talk about smart cities or smart world. Everything is connected and they can talk, communicate, and making smart decisions. So there are many enabling technologies to support such scenario. For example, Internet of Things, AI, machine learning, 6G, all different communication protocols, etc. But also, on the other hand, we want to ask some security or trust related questions. For example, there are so many devices, heterogeneous devices. They work with each other and mainly in a more and more decentralized way. So in those systems or networks, how can we ensure that all the entities or most of them are trustworthy? Or how can we actually facilitate the collaborations among those smart entities? That's a big challenge. And actually, there are many technologies that can help. I believe blockchain could be potential one of those solutions. So for today, I will mainly start by talking about some very basic stuff about blockchain and focusing on those properties that may facilitate later understanding of our work. And also, for today's talk, we mainly focus on the multi-signature schemes we develop over the years, and that can facilitate different parties, multiple parties, to agree on something in common. And I will actually make two example projects and talk about them in detail. So first thing, what is blockchain? We actually can treat blockchain from all different angles, but one of the angle is that we can consider blockchain as a way of organizing the data. And it's actually a chain structure connecting different blocks of transactions. I actually draw some illustration here. You can see the transactions, they are organized in a specific crypto structure, a Merkle tree, so that as long as any transactions, if the content value has changed, or the order among different transactions has changed, then actually that will be reflected on the hash value. And eventually, the root hash value of the tree will be changed so that we can easily detect anything has been manipulated. And only with one block, that's not sufficient. It can only, include limited number of transactions. How do we expand that? Then we need to build this chain structure so that, especially the block header and the hash values of the prior block will actually be included in the next block. Then this way, we can actually be ensure the blocks follow certain order, and anything happens or changes in the prior blocks, the later block, we can check the hash value and detect those changes. So with this structure, we are able to make sure that nothing can be changed once it's actually recorded on blockchain. So that's very important. But only with this thing, it's not enough. Underneath, if we only have a central server who actually hosts all the data, then the server is compromised, still your data may be compromised, right? So we need fundamentally a peer-to-peer or decentralized system. So there are multiple parties, and each of the host machine actually hosts a unique copy. And only when all the copies are identical, or the majority of the copies are identical, we know the blockchain is not manipulated. So it's essentially decentralized system. And also, then whenever we have this decentralized system or distributed system, then how can we ensure, the data, different data copies on different machines, they can be consistent? We need certain ways to do that. That is certain consensus algorithms, and there are multiple of them. You probably can know some of them, like proof of work, proof of stake, and etc. There are many of them. But essentially, we need those multiple parties working together. And then talking about blockchain and trust, several unique properties of blockchain actually enable trust. For example, the non-repudiation thing we just mentioned, because of the specific data structure used to store different transactions, actually we can prevent malicious manipulations of any of the transactions. And when we have a larger system, more distributed parties participating in the blockchain, and also when the chain grows longer and longer, the system becomes more and more secure. On the other hand, yes, it has to be a decentralized system. If it's a centralized system, as long as the central party is changing the data, we have no control. Also, blockchain especially the public blockchains, may be open for validation. So any participants, if you can join the blockchain, that means you can get a copy of the data and you can validate if all the data, all the transactions are correct or not. Okay, so to prevent manipulation. And then last but not least, there are so many different blockchain systems in today's cyber world. And several of them are quite famous or well-known. One is Bitcoin, the other is Ethereum. And also they are public chains, the representatives. But on the other hand, there are also relatively private blockchain. We call them permission-based blockchain. So those blockchain systems are not open to all. So you have to get authenticated so that you get permission to get involved in the blockchain so that you can contribute. And of course, they add additional security or trust to the chain itself. But at the same time, it's less open, less decentralized. So there's a trade-off. When blockchain was first actually attract people's attention, the very famous application is Bitcoin, the digital finance. And in Bitcoin, it actually adopts a simple as script that can allow transactions among different parties. And that is mainly used for digital currency. Then later on, Ethereum actually make this application much broader because Ethereum actually consider the blockchain system as a state machine. So that means there are different accounts or addresses on the blockchain, and each address or account has its unique status. And that state actually can transit from one state to another. And as long as there's certain transaction happens, that transaction will lead to certain state changes. And then it basically consider all the accounts and their current states as one state. And then if any transaction occur, it will actually move the world state from one to the next one. And if we consider it like this way, it's quite similar to the Turing machine, actually. Also, by enabling smart contract, it allows certain logic to be executed. And in this way, it generalized blockchain. So it's no longer just a digital currency system. It can be considered as a Turing complete machine, so that it can be considered as a computing infrastructure to support all different applications running on top of it. So that's Ethereum. So that's very important. But other than those two, which are public chain, there's also permission-based blockchain. For example, Hyperledger Fabric is one typical example. It has strong identity management. That means if a certain party needs to get involved in the chain, they have to pass the authentication process. And it also enabled the endorsement function. So once a transaction, before the transaction can be posted on chain, there are multiple parties, it's typically decentralized. They can actually check the transaction and endorse it. And then for endorsement or for any validation, we may involve the digital signatures to show you actually approve certain things, right? And the default setting is ECDSA, which is pretty classic or like popular digital signature system. And later we'll come back to this again. So by having those infrastructure, actually blockchain enabled a lot of applications. And for example, NFT, which used to be very popular, and also DAO and DeFi and blockchain-based games. There are many applications. And there are also some applications, for example, like supply chain and energy, as we mentioned, and Internet of Things. As long as there are decentralized systems, when people are actually, interested in applying blockchain back like a few years ago, they actually try blockchain in all different type of systems. And of course, there are challenges. So that's why right now blockchain is kind of in a down time. But maybe in the future, if we can address some of the challenges, they will come back again. But anyway, there are many challenges, but one of the major challenges we will talk about today is the digital signature efficiency. So as we mentioned, blockchain requires a lot of digital signature application. For example, in Fabric, we need the endorsements process, like multiple parties, they have to agree on one single message. And then the current endorsement process is tedious. Each of the engaged party needs to provide its own digital signature. So then you have to spend time to collect individual signature from each of the participating parties. That's a collection, data collection. Also, later on, if you need to store those signatures on blockchain, it will be multiple signatures, which are quite long. And also later, if you want to verify the signature, you have to verify them one by one. So the whole process is very time consuming. Because of that, it takes a lot of resources and its lack of scalability. And a promising solution, which will also be the major topic for today, is a multi-signature scheme. So when we talk about multi-signature, the nice thing is, for example, you may engage multiple signers or parties who needs to agree on a certain message. So they need to sign the message. And each of the party will have its own private key and public key. But the nice thing is, after aggregating all those signatures on one message, we can generate an aggregated signature. And the length of that signature is just the same as one single digital signature. So the length can be significantly reduced, especially if you have a lot of signers who have to agree on one message. Also, not only that, the verification process, we only need to verify the aggregated signature. So just verify it once. So that can also save us a lot of time. And also blockchain size, we can significantly reduce the length used for digital signatures. So that's a very nice thing. And that's why multi-signature scheme has been developed a lot with the popularity of blockchain. And there are generally 3 categories of multi-signature schemes. One is RSA-based signature scheme, and the other one is so-called snore-based signature, and the last one is BLS. Later on, we will mainly focus on the one in the middle called snore-based signature. So you can see each of the algorithm has its own unique property. With RSA, it has a much, longer signature length eventually, which is not something we want. We want to have a shorter signature at the end. But the benefit is it actually is based on multiplications. So its time complexity is simple. So that's a nice thing. But BLS on the other extreme end has very short signature length. So that's a very nice property. However, the security of that is based on bilinear pairing, which is very time consuming. Actually, from this black box here, you can see we did a very simple comparison. For one multiplication, it takes the time as only 0.04 millisecond. But for pairing, like the time consumption could be up to 232 milliseconds, which is way higher. So that's why people try to, do a trade-off, right? And Snore signature is something in the middle. So it has a acceptable signature length, which is just double the length of the BLS-based signature, but the time consumption is much lower. So that's why some of our work are based on the second way, the Snore-based multi-signature scheme. So let's briefly talk about the signature. How does it work? So before we move on to the multi-signature scheme, we first start from the basic version, just one sender. So this person has its own public key and the private key. So you can see the relationship. The G is a generation algorithm. G to the power of a secret key of this person will lead to the public key. Then also, this is permanent, but each time when this person needs to sign a message, he will generate a random number R, and based on R, he can generate a corresponding T value. And R needs to be kept secret, while this T can be shared with others for verification later. So then, given the message M, together with T, put them into a hash function, it will lead to this so-called C value, which is constant. Then, based on this particular signing algorithm, then we actually can get or calculate a signature S. Together with the C value, which is constant value, this author or this sender can share this CS pair, which we called the signature. What does it called? Is it sigma, right? This sender can share the sigma with anyone, and then anyone receive this can verify if the signature is correct or not by checking if this condition, if this equation is true or false. Okay, so that's a rough idea. And then that's just one sender. If we have multiple senders, then how does it work? So we assume simply 3 senders, and each one of them has their own public key, private key. And for any given message, each of them will generate an R and T pair just for that message. And then after that, these 3 users, they will actually exchange their T and their T values so that they can get a common C value based on the common message and the common T value. Then each of them can calculate their own S, the signature. And the aggregated signature is quite simple. They just, after each one calculates their own signature, they exchange those S1, S2, and S3. Then the overall aggregated signature just be the sum of all 3, modulo Q, of course. And at the end, the aggregated sigma will just be the pair of C and the combined signature. So that's not that hard. And because of this nice sum property, and Snore signature can actually be verified very simply. And the aggregated public key is just the multiplication of all the public keys from the participating party. Then again, we need to verify if this equation is true or false. Based on, slightly change, this is no longer the public key of one person, it's the aggregated public key for now. So the overall framework is the same, but now we are able to actually integrate the signatures from all different parties and eventually get just the same length for aggregated signature. So that's this, very nice. However, it has multiple problems, security problems. Problem number one is so-called the rogue key attack. Because of the nice, simple public key aggregation. So we can see the public key aggregation is just the multiplication of each party's public key. But because of that, if there are, let's simple case, two signers, one signer is honest, the other is malicious, okay? Then the malicious party doesn't have to have a true secret key and public key pair. This malicious party will only, once it gets the public key from the honest user, it will generate its public key by this simple equation. Okay, it can actually get a random value and then divide that value by this PKY. So the purpose is the aggregated public key actually is under the control of the malicious user. So they can arbitrarily generate this aggregated key. If that's the case, recall that the verification requires the aggregated key. Then for any arbitrary message, this malicious user will be able to replace the message and then still calculate a C value that can actually pass the verification. So with this being said, it's easy to actually manipulate or forge a signature from an honest party. And this is problem number one. The fundamental reason is we didn't check. Well, this malicious user claim he or she has this public key, but there's no way to guarantee this user actually own the corresponding secret key. So if we are able to verify that, that can actually prevent this attack. So that's one thing. Well, the second problem is we call it K-sum attack. This may be a little too mathematical. I will try to stay on top, high level. So basically, an attacker can succeed if there's a malicious endorser who can simultaneously or concurrently open K-1 multiple signature queries, okay, to the honest user. And then the honest users just provide the corresponding signature on the same message. Okay, but each time the random value will be generated as a different value. Okay, so in this case, the aggregated signature actually will be the malicious attackers will actually have K-1 trials. Okay, and each time there's a different CI created, and then for each time also from the aggregated signature, that's the corresponding SI signed by the honest signer. And then at the end, the malicious attacker actually can generate the C star and its own private key using this way, and then try to generate the aggregated signature as this I star. So the goal is that if this C star and the I star can be generated in a certain way, specific way, so that it can pass this verification, then the attacker can succeed. The thing is, what the attacker can control, this random value actually can be, because the attacker just get that value. Well, how to say this? The honest user will not release their own random value R, but the corresponding key value is released. So once the attacker actually repeats this process for K-1 times, it actually can aggregate all the TI value, corresponding TI values. And then it also can calculate the corresponding hash value of that K-1 trials. Then the attacker, all he or she needs to do is to be able to make sure this equation is true. And what the attacker can control is the corresponding TI value and also its own CI value. Okay, so without talking about the details, we will move on. But what this attack shows us is, if there are multiple signers, the last signer actually can, if with excessive power, that's the assumption, can forge a joint signature on a new message, arbitrary message, very easily. And if that's the case, then for an aggregated signature signing process, there's always one last signer. How can we prevent malicious user being the last sender. That's very difficult. So that's the second challenge we need to address. Basically, okay, I show here, these three values can be manipulated by the attacker, but it's not an easy job. Attacker needs to make multiple tries, okay, eventually hopefully can solve that by a limited time. Okay, so that's the whole process. Actually, fundamentally, the mathematical problem is so-called a K-sum problem. Basically, the Wagner's generalized birthday attack is the fundamental mathematical. Given K list of random elements in the real number field, and for each of the list, if the attacker can actually randomly pick, can find one specific value, and so that to ensure the overall C1 from list 1, C2 from list 2, all the way to CK from list K, their sum add up together modulo Q equals 0. If they can guarantee that, then the aggregated signature, which is also the sum of all the hash values, can actually lead to the 0 modulo Q, which will cancel each other. So the the honest user's secret key is no longer required. Okay, so that's the idea behind. Okay, so those are the challenges. So next, we actually will talk about our specific proposed scheme, how we address it. So the first one is we propose a multi-signature scheme that can actually prevent the rogue key attack and the K-sum attack, and also make the signing process more efficient. So that's a contribution. And we actually adopted COSI as the baseline algorithm. COSI is one of the most popular multi-signature schemes based on Schnorr signature. And fundamentally, it follows the same signing process. So it's also vulnerable to those two attacks. And one advantage of this algorithm, for all the multiple signers, they organize the signers in a spanning tree structure. The benefit is a spanning tree is a loop-free logical topology. So you go to one signer and you follow the way all the way down, you can never find a way back, so that you can avoid the loops. And also, there's a single active path between any two network nodes. Because of this, the message can be just forwarded from top down, and that can actually significantly reduce the redundant message exchanges for the communication purpose. So because of this structure, this algorithm is also scalable. So that's a benefit. And what we did is we want to adopt or maintain this structure, but making it less robust against those two attacks. So that's our major contribution. And specifically, what did we do? We adopt a gamma multi-signature scheme. So gamma multi-signature scheme is quite similar to the Schnorr signature, but the major difference is it actually split the signing process to online and offline part. For the offline part, it means you don't need a message, so you can do pre-calculation. So that process actually can be done before the message comes. This can significantly save your time. So that's the online and offline part. But then additionally, how we also adopt the spanning tree structure. Then we have to have our own ways to prevent those two attacks. One of the ways we propose to prevent the rogue key attack is a proof of possession. Remember, you have to show you have the corresponding secret key, so you can claim this public key is actually your key. This way, we can avoid the attacker arbitrarily claim a public key. And another one is to prevent the K-sum attack, we actually improve the signing process. Then also based on the base version, we say it has online phase and offline phase. We later find the original phases, the order actually is not optimal. So we slightly change the order of the signing process and make it more efficient. So that's the major idea. And this is how you can do a proof of possession. I would just talk about it briefly. So for example, we have a signer and a verifier. And the signer say, my public key is PK. But the verifiers say, okay, you have to show me a proof. Otherwise, I don't believe you, right? So then rather than just the public key itself, this signer needs to provide two variables. One, those are actually some calculations based on the public key and the private, the secret key of this signer, and that's a pair. And once the verifier gets a pair, it will just verify the lower equation and see if that's true or false. And if true, that means this signer actually own both the secret key and the public key, that pair. So that's it's not arbitrarily claimed. So that's a proof of possession, and we adopt that in our proposed scheme. So then this proposed scheme is working like this way. Remember that we have all the signers organized in the spanning tree structure, and there are 4 phases. The first phase is announcement phase. So the leader node, which is the red node, the root node, will announce the message that needs to be signed by everyone, so that it passed down following the spanning tree structure to reach all the nodes. And because it's a tree structure, so each node has its own parent and the corresponding children. So it's a top-down way. Then the second phase, we need all the nodes to provide their partial commitment, which is a random value generated. Okay, this is something similar to the R and T value we mentioned in the base snore algorithm. And after that, we call it the commitment stage. After that, then the leader node will also send a challenge all the way down to all the signers. And recall in the basic snore-based schemes, the challenge actually engaged the T value and the message itself. But here in our gamma-based signature scheme, the C does not involve the message itself. So we actually split those 2 parts, so that at the end, the last stage, which is bottom up again, we actually collect the signature. So each child node just pass its signature up to the parent, and the parent aggregate the signature from all the children and itself, then pass it to the upper layer parent all the way up. And you can see in this signature phase, now the signature S no longer just as like SK, the secret key times the C value. We actually split the C value, so it does not involve the message itself, but we actually have the E as the hash value of the message itself. So by splitting them, now if the attacker wants to manipulate C, they have to manipulate the message and the C in a separate process, which will be much more difficult for the attacker. So that's how we prevent the K-sum attack. So that's this algorithm. But now you can check those 2 different ways, 2 different direction communications. The blue part actually do not require the message itself. So now, rather than having the 2 blue parts done, how to say this? Oh, actually, no, sorry. The blue part requires a message, but the yellow part, well, let's see. This challenge does not. Okay, so actually not, sorry, I think I made a wrong label. The first part requires a message because that calculates the hash value of the message. It should be the phase 2 and phase 3. Those 2 phases, they don't require the message. Okay, so because of that, we can actually put them ahead of the message. So before the message arrives, we can do those 2 phases. And once the message comes, we can only do 2 parts, 2 phases. That can save us time in online. So that's how we actually modify the orders of those 4 phases. And because of this, so you can see now these 2 phases are moved up. Then when the message comes, we only need to do phase 3 and 4 now. So that can save us time. So then we did a test. We actually run the algorithm on the leader node and see how much computational overhead we require from the leader node, which is most time-consuming part. This is the yellow one was the basic COSI algorithm, and the blue part is our algorithm. Because we separate the online and offline part, so actually for the leader node, we can for the online signing phase, we can save the time significantly. And it can also is scalable. When we have a lot of signers, say even 16,000 signers, the time is still kind of, much lower than the original COC algorithm. That's a time efficiency. Then we also need to apply it really on the blockchain itself. So we apply it on Fabric. Originally, the Fabric endorsement process required ECDSA. So each signer basically needs to provide their own, signature. But we revised the process. So mainly like this. Initially, the endorser needs to form a spanning tree. And then they will actually send a synchronization to the client. So telling the client, now you can send me the message. Basically, the pre-processing has been done already. Then once a client submit a transaction, basically the message that needs to be endorsed by all the endorsers, then it's an internal process, endorsement process, which is our multi-signature signing process. And after the signature is aggregated, then it will be returned to the client. And the client will then post it on the blockchain. So the major part actually we changed happens here. Okay, so that's how we revised the blockchain. Then we also did some performance tests. So you can see the blue one was the Fabric default transaction process. The yellow one is the revised process, which include both online and offline processing time. So you can see it's quite similar to the original one. But if we count only the online part, it will be much smaller. So that's the performance. Okay, so that's one work. And the next one is we still have some problems. So for example, for Fabric, for endorsement, right? People sometimes may require more flexible endorsement. The default multi-signature supports, for example, there are 3 signers, they all agree on one message. But it doesn't allow flexible ways, for example, the OR logic. It could be like signer 1 or 2 or 3 who agree on, right? So we want to have more flexible endorsement policy that can be supported by multi-signature, which is not happening right now. So in this particular work, we try to implement the monotonic multi-signature scheme. That means we allow the OR logic, and it's also group-based. For example, on Fabric, they actually enable the organizations. Each organization may have multiple members. So for a particular endorsement process, they may require all the 3 organizations to actually sign. But it doesn't matter which member from each organization provide the signature. If an organization have multiple members, say as long as one member sign, then it's okay. So that's the logic we want to implement or support. So basically our logic is down here, our logic is here in the middle. So organization 1, 1 member, and organization 2, 1 member, but it doesn't matter which member from each organization. Okay, so that's the purpose we want to achieve. And in order to achieve that, we propose a group-oriented multi-signature scheme. And also we try to optimize the transaction protocol. So the block size and the verification time can be reduced. Then what we propose is, we propose a smart contract-based solution. Because smart contract can be publicly verifiable and it can be executed automatically. So we can basically trust smart contract to be an honest signer. Recall that previously, we have to implement a relatively complex process to prevent so-called the K-sum attack, right? Because we cannot trust the last signer, the leader node. But now we actually just adopt a smart contract as the final signature aggregator. And because smart contract can be publicly verifiable, so the code implemented there, we can think we assume it can be trusted. So that's a different solution to address a K-sum attack. And then we so that's a process. So you can see we have multiple signers, 4 signers, and each of them can interact with a smart contract. So this way, we also avoid those spanning trees. So each node has to talk to the parent. Now all the nodes, they directly talk to the smart contract. So this way, we can also reduce the communication overhead. Then this is a detailed process how we actually collect the signature. I will skip that. Then another thing is like supporting the OR logic. That's also an important thing we want to achieve. And what we propose is for each group, we actually have the hierarchical structure. On top of each group, basically you can treat each group as one center. So it's the same logic, right? Every group needs to sign. But then down one layer within each group, we may have multiple members. And there we want to implement the OR logic. Okay, so in order to do that, we want to eventually, fundamentally, the core problem is how do we actually generate a group-based public key so that it can represent any member from this group. Okay, in order to achieve that, we actually introduced another mathematical theorem. It's the Chinese remainder theorem. It actually can combine all the public keys of all the members from one group into one identical group public key. But with that group key, no one actually can tell which member participate. So this way they don't know which member actually provide his or her public key. But there is a group administrator in this case, and the group administrator knows everything. That's something we cannot avoid. So with that being said, this is one example. Given a group I, xi, xi1 means the public key of the member 1. Xi eta means the public key from the member eta. But no matter how you actually do that, as long as you can find those prime numbers, and this public key modular each specific prime number eventually can give us the same ki value, and that will be used as the public key for this group. Okay, so with that being said, with this public key, anyone can actually send the message, and the verification process just take this public key for verification, then you're done. Okay, so that's a scheme part. Then we also did some security analysis and some performance analysis. For security, we actually emphasize 4 aspects. First one is unforgeability. So that means the signature cannot be forged by any attacker. We can avoid the K-sum attack. Also, anonymity. That means from each group, which member from this group actually signed the message, that is anonymous. You cannot reveal that information. Then revocability basically means there are senders. The senders can move. They can enter a group. They can also exit a group. But if a sender exit the group, then the sender cannot actually regenerate the legal signatures anymore. So that's also very important. And traceability. Basically, we still have the group administrator in place who actually knows who provide the signature. So in case we need the traceability, the group administrator actually will know who actually provide the signature. So that's the algorithm. Then we also compare it with the another multi-signature scheme, the multi-signature scheme 2, which actually also avoid the K-sum attack and the low key attack. So you can see the signature size ours is slightly longer because the basic version, they only support individual signature. But in our case, we support different groups. And theta here basically represent the number of groups. And with more groups, the signature length will actually be longer. Let's see, this is also the time complexity. So you can see, compared with the basic algorithm for the signing process, the complexity, our algorithm is much shorter. Okay, so that's the comparison. And we also did some performance analysis. In those 2 figures, we actually compare the signature time and the verification time. So the red one is the basic version, the MOSIC, the comparison algorithm, and the green one is ours. So you can see the green bar, especially for the signing process, is much smaller than the red one, although the verification part are roughly similar. So again, then we have to apply it again on Fabric. So this is the original Fabric protocol, transaction protocol. And we actually change it by having the endorse a proposal part, actually we implement those endorsing nodes here, and they actually follow our logic, and they can be managed in groups. So since the proposal scheme introduced smart contract, we install those smart contract on the ordering nodes, and endorsing nodes needs to interact with those ordering nodes so that we can actually aggregate all the signatures. So that's a change we made. Then we actually did one case study. There are many cases, but we did a simple one. We actually introduced 10 different groups, and each group, we assume there are 2 members. And those 2 members, their logic is OR. So basically any one of those 2 members, as long as they can sign, this group will just basically sign the message. Then we actually implement the whole process. And here's the experiment result. You can see the block size and the verification time. We actually did a comparison with our algorithm and the original protocol. And you can see our algorithm outperforms the original one. So that's the experiments. Okay, so that's the tool works. Hopefully I didn't cover too much in depth for the math part, and hopefully you still understand the overall logic. Okay, so again, this talk, we mainly focus on the multi-signature part, but actually there are many other relevant domains we can apply blockchain. Some of our ongoing work include, we also apply blockchain for autonomous vehicle networks, where different vehicles, they need to communicate with each other. So we want to make sure the message exchange and the data transactions, if they're doing any trading, is also made fair and non-repudiated. And also transactive energy trading, as we mentioned before, we actually have an ongoing NSF grant supporting that. Other than that, we also did prior work for Internet of Things for each of the specific IoT device. Actually, it needs to frequently perform software updates. But for those devices, they are typically resource limited. They don't have enough power, memory, storage to actually do the authentication. Then if arbitrary users send in software updates, how can the device know it's actually from an authenticate user, manufacturer or not? So we actually offload that complex authentication process to the blockchain. So that's another work we have done before. So there are actually many other domains we can apply. And yeah, there's more to come. Okay, that's all. Thank you.
I have a question for you.
Okay.
The GMS, with the asynchronous verification, is that for the single contract? Can I hold that for a token length for additional verifications, or do I have to do it for each contract? Is there a persistence in that verification?
So yeah, so for the verification, if multiple signers, right, they signed the message and it's one signature, you only need to verify it once.
Okay, but if now I have another contract with that same member, can I use that earlier verification to prove it's really that member, or do I have to restart the whole process?
So depending on the message you want to sign, if it's a different message, then you have to resign the message.
So it's not persistent across messages.
That's also a way we want to ensure it's like you actually check the message and then you sign.
So would I have multiple messages for one contract? Potentially, so I could have it persistent across multiple messages.
Oh yeah, okay, right. So say if you want to provide an like signature for a sequence of messages, right? You can still do that. The message is an abstract concept. As long as it's the same contents, everyone needs to agree on. Right? Yeah, you can do that. Yeah.
So you mentioned that you grouped all public keys as one
Mm.
main public key.
Yes, right.
So whenever you get a message signed on using that public key, admin public key, you call anyone within that group can use their private key to open the message. How it works?
It's not for any to use their own like private key to actually open the message. It's just like everyone. Okay. Everyone has you can understand it this way. Everyone has part of the control, basically their own private key, right? They can send the message, but overall, only all the parties agree on this. Everyone signs. So then there will be an aggregated signature generated. Okay. And if say you have your own key, you cannot have you don't have control over the aggregated signature. You cannot actually forge a signature. That means you have your own private key, right? You cannot generate a message and also create the aggregated signature. So say all others agree on, that's something you cannot do. Does that make sense? You don't need to decrypt the message. The message is not private. It's open to all for everyone to verify if that's true or not.
It's a quite lot. Maybe probably
Too much, maybe.
go through the question.
Yes, please.
And one more thing, you had comparison. That
Yes.
is comparison from multi-sig, like Ethereum has a multi-sig smart contracts which can do, or else you did the comparison of Fabric, hyperledger Fabric.
So Fabric itself, by default, it doesn't have like a multi-signature. Yeah, but it's, I think, about the process to adopt. But what we compare, because there are also other multi-signature schemes proposed. So we are comparing with those works. So those are state-of-the-art works. Yeah.
Nice.
Yeah, no problem.
On the comparison, so combine the two questions. That the system might be another sort of experiment we can run. Because, if it's the same sender or receiver, then there can be a level of persistence that further reduces the time.
Yeah, so right. So we can consider that, right?
Yeah.
Maybe that's another way we can test our algorithm. Yeah.
And the speed up or the scale of what's the speed up of the performance? Well, how many times is improved by items?
So it's this way. If you are saying the this one, we actually split that into online and offline. So the online part can be significantly reduced. So this is if I remember, yeah, this is a log. The y-axis, yeah.
Yeah. Yeah,
Thanks. And yeah, feel free to contact me offline as well. Here's my contact info. Yeah, let's connect. Yeah. Okay, so I think that's all right. Are we done?
Oh, yeah. Yeah.
Okay, thank you.
Thanks everyone for joining, and thank you, Daswin and Yuhong, for excellent talks and a lot of information. We will also share some pointers and also their research work information. After this call, we'll send an email linking all their research papers on the discussion, whatever we had today. So thank you so much for everyone. Appreciate it.